So today we'll be talking about data structures and their applications in competitive programming. Just a quick preface, we will talk about a lot of different data structures in this lesson, and some of them are going to be more abstract. So this requires definitely some basic knowledge of how arrays and how lists work. So if you're familiar with lists and input like the previous lessons, then you should be okay with understanding different data structures. If you're unfamiliar with that, it's completely fine. We'll go slowly so you can understand. And if you do, that's even better because a lot of data structures are based on lists. And yeah, that was my preface. Now we can start the lesson.
Well, so we were first about to talk about what a data structure is. It's like when you have, say, an integer variable, you only can store one piece of information, and when you want to store multiple pieces of information, you use a data structure, which are like lists, DQs, queues, and all sorts of things. And they're really useful because a lot of times you're going to need to store more than one piece of information at a time. So we really want to point out the importance of what data structures are. And as you can see, Jerry drew a very helpful example to show you where, say, the int x can only hold one value, but a list can hold like 3, 4, and 5 all at the same time. Where so so integers are a lot more limited than a list, right? And most data structures. So we want our first one, we want to talk about stacks. Stacks are like if you have a stack of plates, as you can see in an example, you only can add things on the top and take things off the top. So when you say look at an example of the image, we show how it works is you only can add to the top and you only can take from the top. And there are append, which is an operation that can add elements to stack, and pop, which is also remove elements from a stack. You can think of it as technically a list, but like a very specialized list with restrictions on how you can remove and add and look at objects. So we have a short example for stack here. Think of a stack of books. As you can see, we have Pride and Prejudice, Anne of Green Gables, and Harry Potter. And there are ways to look at a stack, look at a top book of a stack without removing the object itself. So these are some practice problems if you want to try it.
One comment on stack implementation is that I just kind of want to explain this line because the first few lines are pretty easy to explain, right? You can add stuff, you can remove stuff, and you can print out the entire list. This is kind of like printing out. We're first of all implementing a deck, which is basically a stack. You can print out the stack, you can definitely append and pop, but one thing you have to realize is that you can actually you can actually view what's on top without removing it because otherwise you would have to delete it and then view it. But what you can actually do is that there's actually a way to view this. I think in other languages it would be dot top or dot peak. That's how you would do it in other languages. But in Python, it's actually really cool because acts like a list, so you can actually view the top element without even removing it, which is really cool. All right.
And very useful.
Yes.
So those are some stack practice problems if you want to try them.
Yes, and we will come back to them later.
One of them in general. Okay, so now we talking something about queue, which is you can think as a line where obviously elements will go in from the back and then come out the front. So you only can the first element is in the front, and you only can view and remove the front element at a time. So you can append left, which is add elements, and pop, which is remove the front element. And this is kind of useful when you want to say simulate what a line would look like in coding. So we have a little implementation here with 3 of the execs in a line, and we have first, then we have Jerry, then me, then Ryan, and then we can look at who's in the front of the line. and then we can remove whoever's in the front.
Yes. Again, you see that we actually both times we actually import something called a deck. A deck is very similar to a stack. If you want to input, use either a stack or a queue, just do the same thing. One thing you should notice is that a queue is really similar to a stack. Because remember in a stack, we had append and remove and view, right? This is kind of the exact same thing, except before we could only pop from the top. Now we can actually push from one side and pop from the other side. So in a way, a stack is kind of like a queue, which is also just a glorified list data structure.
Yeah.
Yes.
So we have Dec or DQ if you're want to pronounce it that way, or which is basically like a stack and a queue combined, where it's a double-ended queue where you can remove from either end and add from either end. And we have a little important chart there to show you what are the operations to add to which side and how to remove from each end. And this is basically a queue but better, and can be a lot more functional than a queue and a stack. So generally you would want to use a deck. And see, these are some more commands and methods that we didn't mention specifically and have their own descriptions. So when we share the slides with you later after the meeting, you can read and have a more detailed explanation of what each function does.
Yeah, again, I just wanted to highlight some important ones that we didn't really get to during lesson. We learned append left. Clear is kind of important because sometimes you want to clear the deck to use it again. You don't have to initialize another one because that takes up a lot more memory than if you just cleared it. You can actually do count. This is actually, I feel like this is the most important part of the deck. And this is this is used in like a lot of problems where you have to where it's like stack and a queue problem, but then it's also using like a different type of data structure as well. For example, one example would be a monotonic queue, and you would actually have to use a count method, which is actually counting the number of elements equal to X. If you were to do this any other way in a deck format, like using a list, it would be a lot slower and it wouldn't be a very efficient data structure. But because we have a deck, it can actually pop and push perfectly, and it can also save all the element indexes, which is really cool. Uh, Extend, yes, that we talked about these. All right, the last one was reverse. You can actually reverse all the elements. This is pretty cool. It's kind of like sorting, but you can actually reverse all the elements in a deck if you wanted to. Basically, if you had a stack, if you reverse it, you technically treat it as a queue. All right, so.
Okay, we have a basic implementation of a deck right here.
Yeah, because a deck is that similar to a queue, we decided to just implement a stack and a queue, right? Because a deck is literally the same thing as a stack and a queue combined, like what Matthew said.
Yeah.
Cool. All right.
So now Jerry is going to talk about a specific question we had for practice stack problems.
Yes. So the problem I want to talk about, I'm just going to tell you where it is this question. So the Geneva confection. So if you want to, you can take a look at the question for about maybe 1 minute or so. I will post actually the link in the chat if you give me a second. All right, so if I go to the chat, I'll post a link in the chat. I think this is the link. Yeah, it is.
Uh,
Oh, I posted to you.
Oops.
Yeah, so here's a link. Take a look. You can take a look at it for maybe about 1 minute, and then we'll talk about how to use what we learned to do it. It might be a bit easier because you kind of already know what you're going to use to, like what data structure you're going to use. On a contest, it might be harder because you're not told what data structure, but it's also an S3, so we thought that it would be kind of difficult to solve just by your own intuition. So yeah, it kind of balances out. So try the problem, take a look at it, and then in 1 minute we'll take up the solution using what we learned. Cool. And also here's a problem statement again, just here. If you have any possible ideas about how to solve it, you can put it in the chat, and we will discuss them as well. Keep index variable. Compare, okay, compare to next cart and cart in branch. If not, next cart slide it to the branch. Okay, let me think. This is very detailed. I need to
Yes,
give,
I
yes,
believe you.
I I think you're right. I just need 10 seconds to think if it's right.
Yeah,
Like,
I believe he is right.
yeah, it's probably right because you probably solved it already. But I'm just trying to
Yes.
think about it again.
Mm,
Oh, well, you have card in the branch.
yeah, I thought that wasn't the complete solution.
Well, cars in the branch would technically be the same kind of solution, but I feel you're on the right track. You would probably pass most of the test cases. I don't know about corner cases because there might be some, but you're definitely on a very close track to
Pretty
the,
close, yeah.
yeah.
You
You're,
want
you're on the track. Yeah, you just
to
need to get to the oh,
get to the lake.
yes, you need to get to the lake. Maybe you're on the branch right now. All right. So let's really quickly, we'll discuss the problem statement and then we'll think about some ways to solve it. And then again, in like 1 more minute, we'll explain the solution. So first of all, the problem statement, right? So there are cards numbered 1 to n. They're lined up at the mountain top, right? So they're all lined up at the mountain top. That actually answers your question because they're all lined up at the mountain top. None of them are on the branch. So you can do two things. You have a branch here that you can actually slide out stuff to the branch and into the lake, right? So you can do this, whoop, you can do this, and then like this. You can also just slide them all into the lake. I have no idea why you would want to slide carts into the lake, but sure. And what you want to do is that you want to slide them all into the lake so that they go in the exact order of 1, 2, 3, 4, right? So the hint I want to give for this is that this is probably not that much of a hint because we already talked about the data structure before, but if you were to think about this on a contest, you would think about what is so, specific or different about the configuration 1, 2, 3, 4, right? What is so specific or different about the configuration of 1, 2, 3, 4? And so how would that be important to the question? Yeah, I was just thinking of something to say, but yeah. So how is 1, 2, 3, 4 important to the question? And then again, how would you implement it once you know what data structure to use, right? And also think about the configuration of the branch as well. Right? Even though there's nothing in the branch, there are going to be things that are going to be pushed into the branch. So we actually have to think about this as well. So you have to consider both how are cars getting pushed into the lake and how are they getting pushed into the branch and what kind of configuration are possible. Yeah. as y rather than a sideways t.
Mm,
Mm,
I,
wait, so like, not, I think you're right. I just need, so like, you mean like this?
yeah, he want to think about. Mm,
Hmm. That would work, except the only kind of downside I see is that you're not really this is only like one end, like only one endpoint. It would work for this question for sure, but I think you should like actually consider this path as well, because if you do this, you're considering that it has to go here and it has to either go here or here, which is, yeah, you can consider as a y too, but the t, I feel like it shows all the possible paths, like here, here, and here. Uh, to the mountaintop and the branch going down to the lake. Wait, let me. Oh, okay, you're drawing. Sure, go
yes,
ahead.
I am drawing. I think it's more like, say, think of a like more like a glass, like a martini glass. Actually, see, you can see there's the branch
Oh,
here.
is that what he means?
Yeah, I think it's more like like a glass than really a Y or a T, because for like a T you don't really consider the connecting the
Yeah,
mountaintop
that's
to the
true.
branch.
Yeah.
So more like a martini glass.
Oh, that. Oh, that. Yeah, that could work too. That kind of looks like a martini glass too, but I feel like Matthew considers, this endpoint going to this endpoint and also going to this endpoint, and this also looks like a stack. What I think you could draw is also connect the ends like that, so you actually know where it's coming from, where it's going to, and where it can stop at.
Actually, mm, I think actually no. I think that the best solution, just think of it as a triangle.
True. I
Like a
mean, a
mountaintop
martini
here.
glass is literally just a triangle but extended, right?
Yes, but this is
Yeah.
I think even more easy to think about. It's just literally a triangle.
Yes. Think of it as this. All right.
What is that?
It's. Don't worry about it. Anyhow, what happens with duplicate numbers? Okay. So
Oh,
let's go back to the question. There are cars numbered 1 to n. Can there be duplicate numbers? I wonder if there can be duplicate numbers at all. I wonder if you even need to consider that case. No idea though. I think you should go back and try to read the question again so you can see that. And the answer to your question is no, because it's 1 to n, so there are no duplicate numbers, right? It's okay if you didn't see it. Next time, just make sure to read the question like 10 times and don't be me and be really dumb on the CC and not read the question properly and spend 30 minutes doing an incorrect solution. Oh, it's in the sample input?
let me.
Wait, it is?
Oh, okay. I
Yeah,
see. I see. Okay, I see
yeah,
what he means. Okay,
yeah.
so what's going on is that if you read the sample, the input specification, it's actually, although it looks like there's multiple using multiple, actually two different cases that you're considering at a
Okay,
time.
okay.
First number would be how many cases do you think of? Then the following would be one number, which would be how many carts there are, and then it lists in some order. Then another one would be how many carts there are, and then list them in an order.
Oh, right. Oh,
So it may
multiple
look
test
like they're
cases.
duplicate numbers, but it's actually multiple cases you're considering one input.
Yes. Oh, so there are multiple test cases. Okay, that makes a lot more sense because yeah, if there are multiple test cases, like let's say there's 3 at the start, I'm gonna have like one test case of numbers and then another one and then another one. All right, I think that's enough discussion. Unless anybody has any other questions, we'll start discussing the solution. Yay! All right. So here's your first big hint. You can probably finish solution from here, but basically what this means is that the mountaintop. Think of the branch as it's really, really the same thing as the plate structure, or think of it as think of just as a list. I would even just think of it as a list first, right? Because you can push stuff to 4 and it gets pushed into the branch. If you push the next one, it gets pushed to the back, and then you can also pop it out. So it's kind of like a bunch of plates, right? You can push a plate to the back, right? And you can push one plate in and then another plate and then another plate, and then you pop one of them out. It's kind of like the stack queue structure, right? The deck structure that we talked about. The only difference is that in this Dec structure, we're pushing to the back, right? So we have to push stuff through technically you're pushing through the back, right? Because what happens is that you have 4, 1, 3, 2 if you were to push them all through. So technically you would be pushing them 4, and then 1 would go on in the front of 4, and then 3. So you'd push them this way and then pop them this way as well. Kind of like the stack. All right. So what you would do is that let's consider this test case, right? Because the only way we can figure out how to solve a problem is if we consider a sample case. So here we have the mountaintop, we have the lake, and we have the branch. Here's our starting position. From our starting position, the next thing we would do is we would first push forward to the branch. Because why do we push forward to the branch and not to the lake? Because if we push it to the lake, we immediately fail. Because we have to make this 1, right? We have to start with 1. If we push forward to the lake, we immediately lose. And we can also keep track of what the next one is. The next one is 1. All right, so what do we do with 1 then? First of all, we push the stack, push the 4 to stack. Next, we push the 1 to lake, because 1 is exactly the final configuration we want. We want 1, 2, 3, 4, and 1 is perfectly here. The next number I want in this lake is 2. But 3 is not 2, so what do? You probably can guess I push it to the branch because it's not 2 and I don't want it. So I'm going to push it to the branch. So what do you think we would do with 2 this time? We would push it to because we would push it to the lake, because next equals to 2, right? And 2 is exactly the one we have. So we would just push it to the lake. Let's see if that's what we do. And yeah, we push it to the lake. Now, finally, we have nothing else in the mountaintop, which means we have to push everything from the branch into the lake, like that. So let's reiterate that one more time. We start with 2, 3, 1, 4, original configuration. We first look for, the first one we want is 1, but 4 is not 1, so we're going to push that to the branch. 1 is the one we want, so we're going to push it to the lake. 3 is not the one we want, so we're going to push it to the branch. We're going to push 2 because that's the one we want, and we're going to insert everything from the branch back into the lake. Now, my question is every single possible starting configuration possible to go into the lake in the exact order? So is every single configuration possible? Anyone want to try? It's simple yes, no. Is every configuration possible? No. Okay. Why? Quick explanation of why. Or even just any one that doesn't work. If yeah, 3 and 4 switched. Exactly. If 3 and 4 switched, then you would have 4 and 3, and you wouldn't be able to push the 4 out without pushing the 3 as well, and this would cause an error. And the reason for that exactly is that if you have anything in the branch that doesn't match any subset of the configuration, it's going to cause an error. And now what we have to figure out is, how do we write the algorithm for this, right? How do we figure out if it works? Well, let's look at our general algorithm again. We keep a variable called next, which is what we want to insert from the mountaintop. We check each value. If the value is the one we want, or next, we push it into the lake. If it is not the one we want, we're going to push it to branch. And the next thing we're going to do now is we're going to keep pushing stuff into the lake or the branch until we run out of places in the mountaintop to put, and then we slide everything from the branch into the lake, and we hope that it's the right configuration. If it's not, then probably wasn't the right answer. Wait, what was the DQ module called? Let me, I can go up for you, but I'm not too sure what you mean. I think he means the this thing.
Yeah, I believe you mean collections.
Collections.dec. Oh yeah, to import it. So basically you do from collections import dec, right? So that you're importing from collections. It's the same thing in Java, I think. It's just collections.dec, which is, yeah. So it's from collections, you import the dec import, and then you create a dec called anything. You don't have to call it Q. You can call it Martin if you want, or anything. Doesn't have to be Queue. Just name it as something and then DQ with empty brackets, initialize it, and you append stuff. All right. So if I go back here, does everybody understand the algorithm? Let's run through the algorithm again with our test case, right? So first of all, we see that 4 is not, first of all, we have a variable connects to the start, which is 1, and we see that, oh, 4 isn't 1. So what do? We push it to the branch. And then we see that the next is 1. Is the next value on the mountaintop 1? Yes, then we push it in. Is the next value 2? No. Well, we're going to push into the branch. Is the next value 2? Yes, we're going to push it in and increment next. Every time you have a correct value, you're going to increment next. And now you have next equals 3, but there's nothing in the mountaintop. So you're going to slide everything from the branch into the mountaintop, and then you're going to check if it's a correct configuration, and in this case it is, so it's the right answer. Yes or no? So what you can actually do now is that here is the Python code. You can take 1 or 2 minutes to, Matthew, do you want to explain it?
Oh, okay, sure. Okay, the algorithm I used here is actually slightly different from what Jerry described, but it's pretty similar. Well, first, we have all our, next, branch, mountain, and we take in the values. So while we have next, which is the what number we're looking for to be pushed into the lake, and while it's less than the amount of numbers we have, we want to check and keep going. So we want to see first if the mountain is not empty, obviously, and then mountain, the top value is what we want. If it is what we want, then we move it into the lake and we just increment next and remove it from mountain. So now we do a little optimization here. Instead of just inputting everything that's not the value we want into branch, we check branch first, see if the branch top value is what we want. If it is, then we increment next and then get rid of the top value of branch. Now, otherwise, we would just move the the value from mountain to branch and then continue. And at any point where we can't, if there's no value that's what we want and we can't move on, and there's nothing in mountain, and we would just leave and break. So then by the end, we have to check, has next moved all the way to the number we're looking for, which is one bigger than the amount of the n. So then if next is equal to that, then we print yes, we can do it. If otherwise, then we print no, it's not possible.
Very, very great explanation, Matthew. As you can see, there are multiple ways you can solve this question, right? You can solve it my way or Matthew's way. It doesn't really matter. As long as you can get the right answer, you can write the right implementation for it. You can interpret the question again in different ways. For example, I like how Matthew here, he actually breaks out as soon as it didn't work, which is very smart because that saves more time. As long as one of the configuration isn't right, you immediately break. And also at the end, he actually checks if next equals n plus 1, meaning that instead of checking the final configuration, he just checks if the next value considered every single train that came in, and they're all in order. So here's also a pseudocode kind of explanation, and here's the solution here. So again, the explanation is if the first card of either the mountain or branch corresponds to the next number of the lake, you're going to dump it into the lake, right? You're going to push it if next is correct. Otherwise, you're going to slide the card from the mountain into the branch, right? Remember, because it isn't right, so we're going to slide into the branch, and we're going to do that again. If the mountain doesn't have any cars left, right? Because the mountain, we have to check that the arrangement is possible or impossible, because if there's nothing left, if the mountain doesn't have any carts and the branch things don't match up, then the configuration would be impossible. So we'll just stay here for 1 more minute. If anybody has any questions, again, feel free to ask. And then in 1 minute, we will move on.
Oh yeah. Oh, also quick note about my code. You might notice how next is not actually the word next, and I would have made it the word next, but that's actually a word that command that Python uses, so I can't name it next. So just a note, a
It's a
keyword.
reserved, it's a keyword, because next is actually really, it actually does something in Python, so you can't name it something next. Or you could also name it NXT.
Yeah, but it's basically the same thing.
Yeah, NXT looks cooler though, because that's what I use.
No. Okay, sure.
Keyword, yes, it's a keyword. Martin is a Python god, as you can see.
He knows all the terms.
I know, right? We were talking about rejexes the other day.
Oh, amazing. Rejects.
Absolutely amazing.
Not very fun, but sure.
I agree, they're not very fun. Anyhow, these will be posted, right? These slides will be posted. So if you don't understand, feel free to read the slides after the meeting, or if you have any other questions, feel free to ask in the Discord server, and we will respond. All right, so let's move on because we're kind of short on time, and we want to finish all this by the end. So here are the last few data structures, right? So first of all, we have a dictionary. Now, a dictionary is literally like a regular dictionary. It's kind of like a regular dictionary, except it it creates a relationship between two different pieces of data. What that means is that it maps one value to another value. In other languages, it's actually called a map. It's not called a dictionary, but in Python it's called dictionary. And the way you imagine is that every value corresponds to some other value. If you guys have learned functions before, it's kind of like a function, right? Where one x corresponds to one y. This may bring back bad memories for some people, but
Oh no, bijection.
yeah, injections and bijections, surjections. But yeah, so if you have a set x and a set y, you can kind of inject one set onto the other one. That's kind of the definition of a set of a dictionary as well. And each value can correspond to one other value, and it's stored as a key value pair. This is important because each key can only have one value, just like one x can only have one y. And a key value pair basically is stored like this. And you have, for example, Matthew and his age or his IQ level, which is 3.
Wow. Okay.
And his access to a value and you can access the value by specifying his key. So if you go like, let's see, this is called IQ, right? And this is Matthew's IQ. And then you can call that you can go IQ and then you can specify his name. So Matthew. Oh, right. This is also a string, by the way. That Matthew is a string. Before Martin makes another witty joke about some error, this is a string. Yes. So what you can do is that a simple application is a dictionary that maps each city to its baseball team's name. For example, the Rockies would be in Colorado. So if you wanted to see the MLB team in Colorado, it would be the Rockies. If you wanted to see the uh, team in Boston, it would be the Red Sox, and et cetera, et cetera. So there are lots of, as you can see, there are lots of different applications for dictionaries and maps. Yes, that would be the error. And it's also really useful in some problems where you want to map an index. For example, there are an advanced type of problem. You don't have to know this. It's okay, but it's called coordinate compression. When you want to take a bunch of coordinates and compress them into less values, you can use a dictionary to do that, because a dictionary isn't like an array where every value has to be mapped to one index. You can map specific indexes to specific values to, one, save space, and two, save efficiency. So there are multiple different reasons why you would use a dictionary, and it's one of the most commonly used forms of data structures in CP. And I think it came up on the junior too, like some year. I think it was either last year or the year before that. It's pretty cool. Here's some dictionary methods, courtesy of Matthew, that he definitely didn't copy from W3 schools. Anyhow, here's some more important ones. You can copy the dictionary, which is pretty cool. You don't have to do a list comprehension or a list implementation. You can just copy it. Lazyology rules. You can return a dictionary with the specified keys and value. You can return a dictionary, right? That means that you don't, like before, if you were doing a def, you would have to return an array, but now you can return a dictionary, which is really cool. Yay. And you can return the value specific key. Get is the most important one because you can get the value of something. Here's some other, most of these other ones are miscellaneous, like items and keys. Keys is useful, but I haven't seen item used as much. Also, there's update and values, which are also pretty important. These will again be posted. If you want to practice these, I would recommend you just take a dictionary or take any problem and just implement a dictionary, or whenever you want to even use an array or or a stack or any other data structure, you can just try to use a dictionary because honestly, why not, right? It's kind of same data structure, and you can practice these methods, and if you get really good at them, uh, a lot of CP problems will become much more trivial than you thought. And here's an implementation of a dictionary of presidents and their birthdays. Here's an example of a picture of, definitely not photoshopped anyhow. Here's the birth date of Barack Obama, Donald Trump, and all these random people that we definitely don't know who they are. All right, so first of all, you can check if a key is in a dictionary. So you can actually check if Barack Obama is in your dictionary of famous people. I mean, if they are, you can print it. This is important because if you don't do that and you print Barack Obama, you might cause an error or you might just get null, which is also bad because
Okay.
anyhow, in CCC, it's not good to know something that's unspecified. But this actually tells you whether, uh, basically, if a key is in a list. Oh, were you about to say something?
Oh no, it's
Oh,
fine. You can.
okay. Wait, no, if you were supposed to say, you can go ahead. Go ahead and say
Oh
something if you needed to.
no, no, nothing, not really.
All right. When you say not real, I feel like you want to, but anyhow. For name and birthday, you can list every person's name and then their birthday, right? So this is how you access it. You can access for every single key and value. That's how you get a key value pair. Uh, as you can see here, we actually haven't used a lot of the methods because methods are more in harder CP problems where you have to do stuff quickly, like get a list of keys or get a list of values. If you just want to do it regularly, you can easily do a for loop and do an in keyword to get all the to enumerate the list and just get all the values. And again, you can delete stuff, right? Or you can delete an entry from the dictionary, like always. And the last one, second last one actually, is a set. What is a set? Well, a set is a array data structure which is unordered unique elements. What does that mean? That means every single element in the array is unique. You can have these many different types of data types like tuples, strings, integers, doubles, blah, blah, blah. But what this means is that think about it as you only have unique elements. So if you have 1, 1, 2, 3, 3, 3, what would happen is that you would delete all the threes and delete all the ones, and you would end up with a array with singular same with all the elements that are unique. Right? So these can contain again different data types, but how they work is that basically you contain one element of each type. These are useful in questions where they say no duplicates, or they sometimes they actually, yeah, well, one type is where they say no duplicates, but another type of problem, which a lot of people don't actually know to use a set, is when they say this will contain duplicate values. For example, in some array problems or some graph theory problems, they will actually say that, okay, we will give you duplicate values. And CC sometimes does this, and it's really annoying to deal with. But if you use a set, you can bypass a lot of these really annoying things, right? Because if you have duplicate elements and you really don't want them, you can put slits. I solved the problem, but my code is a mess. Oh no, spaghetti code. That happens to everyone. Don't worry, because when you try to solve a problem and you just write random stuff, your code just
Speed,
becomes spaghetti code. Yeah,
speed solve it. It'll take a while.
yeah. So for a set, what was I saying? All right, if they say that you're going to give duplicate values but you don't want them, you can basically take them and uh, push them all into a unique set. Yes, try, accept, pass. Nice. All right. So again, same structure. Here's the methods. These methods are a lot harder, and I'm not going to explain all of them. The difference is because you technically don't even need all of them. Uh, a lot of these actually are used sets because are used for actual mathematical sets, like power sets and stuff, subsets, power sets, supersets. Um, and we don't actually use sets in CP for those kinds of problems unless it's really, really hard, like CCO level. For regular junior and senior contests, sets are used in a regular fashion to remove duplicates. That is almost always what a set is used for. So we don't actually have to, unlike other ones like dictionaries or stacks, it's always good to know all of them, right? But in sets, it's not necessarily great to know all of them. Obviously, you should, right? It's great if you want to learn extra stuff and just if you're bored and just want to learn stuff. But if you want to actually prepare for CP and CC, then you only have to know a few of them. You only have to know how to add, how to remove, how to find the size, just a few of the really important ones that we're going to highlight, right? So if you want to look through these, go ahead. But on the next one is going to be an implement, but we're also going to show you the really essential ones that we need. Only the essential ones, right? Some of these like difference update are just not useful at all. So for set implementations, let's create an empty set. And as you can see, this is literally how you create a set. For most of these, you don't actually need to even import anything because it just acts like a regular thing. All right. So you can add elements to the set, right? So this is a set of deities of some culture. I don't
Egypt.
want to Egypt. Yeah, I didn't want to butcher it, so I was just gonna say deities of some culture. I was gonna butcher it and say almost. I almost said Greek.
Oh my God.
So, as you can see, these are all Egypt gods except Zeus, which is a Greek god. If you didn't know, if you read Rick Riordan, you know that it's not a
Yes.
yes.
Up tier book series.
Yeah, very cool. So what you would do is that, oh no, you added the wrong name. So we can also remove stuff, right? We added all these people. We can remove Zeus because we don't like him or he's just not relevant. And what you can do is that you can also add a duplicate element, but watch what happens. Nothing happens, right? If we have a set of 1, 2, 3, and we add a 1, that 1 is just going to disappear. Because what the set automatically does is that it looks for all elements and it just removes all duplicates at every single step. It works like a binary tree, right? So if you add a single leaf to the binary tree and it balances itself, that leaf will just be deleted. If you understand what binary trees are. If you don't, it's fine. But what basically happens is that it balances itself at every point, so it removes all the duplicates, and when it does, it will update. Reroute, and it will delete the one that is added because it was a duplicate. So adding a duplicate does nothing, because in a set you don't want to add a duplicate anyways, right? And if you add a duplicate, that's completely fine because it just won't be in there. And you can also print, right? Remember, to print almost anything, you just do for I and something and enumerate it. That's usually how you enumerate and go through a list
Yeah.
or set E. Any questions? If not, we'll move on to the last data structure, and that's it. Uh, so the last data structure will go for today, and then that will be it. So I'll just continue with the last data structure, and if you have any questions, put them in the chat, and then once I explain it, I'll go back and answer any questions. All right. So the last one is 2D arrays. 2D arrays are an array of arrays. Whoa, that sounds deep. So you guys know what lists are, right? A list is just a set of elements, set of normal elements, right? And what you can do with this list is that you can actually make a list of lists. So like this, you make a list of lists. And each list element also contains different values. So think of it as a row and column, right? Think of it as a coordinate grid. We talked about the we didn't talk about this, but you probably learned the Cartesian grid. Now this is kind of like what it is, right? 2D lists, or I actually want to specify that this can go up to ND. This doesn't have to be 2D. But more than 1D lists, more than 2D lists might be confusing to understand. But what this is, it has two indexes that point to an XY value, right? So for example, column 2 and row 2 corresponds to A11. Important note, it's actually AX minus 1, Y minus 1. That's really important because if you don't do that, it's going to access the wrong element. A lot of times, like even during contests, certain people accidentally write A34. The problem with doing this is that this actually doesn't exist because row 3, column 4 is actually A23 and not A34. So you're going to get an error here. And you're probably not going to figure it out because you're coding really fast and you don't see it. So make sure that you remember that it's subtract 1 indexes. It uses an XY style to access elements, and an example would be coordinate grid. All elements also must be the same data type. You can't say A00 equals to Matthew and then A12 equals to 3. That doesn't work because they're not the same data type. It just doesn't know how to work with it because what if you say sort? It's going to go crazy, right? So to initialize, you can do two things. You can either do a list comprehension, so element for j in range y, for I in range x, right? So you can basically enumerate every element using a list comprehension. This is probably Martin's favorite topic in Python. Or you can do list equals to 0 times 10 times 10. Very simple. The size, so like let's say this would be 0 times 3 and then times 4, which is basically a 3 by 4 array. And that's really simple to do because you can input an empty array all with zeros or whichever element you want. And it's also okay if you want to change it. Like if let's say it's 0, but you actually want to change them all to 1. Don't worry, you can just change them all. You can do a for loop. And to access them, it's really simple too. You do a for I and then a for j in range. So you do a for I and a for j, right? And then that would basically loop through everything. And think about it as you're looping through the rows, and then for each row, you're looping through the columns again. So that's how a 2D list would work. All right. And the final one are 2D array methods. Now, the only method that we really need to talk about is how to rotate a list, because most problems considering lists, especially in CEC Junior, simple senior, consist of rotating lists. If you did image rotation like Young, I don't know if he's here, but if you did image compression or rotation, or I think Martin did it too, but if you know that, then you kind of also know how to rotate a 2D list or an array. What you do is that you basically go, like if you want to rotate 9 degrees, you go grid y, x minus side length minus 1. Think of it as this element gets rotated by 9 degrees to this element. So you're actually rotating it like this, or you can rotate to the corner. And every other element gets rotated in a similar fashion as well. So when you're rotating an array, don't forget that, like, let's say it's a 3 by 3 array. When you're rotating this one, rotate the entire array and figure out where the corresponding value of it is after rotating 9 degrees. And then you would write out the coordinates. Like if this is 0, 0, right, this is 0, 2, and then you would keep 0, 2, and then you would keep rotating every single element and try to find a pattern. And here's the pattern. Again, we summarize it here. So it's grid y, side length minus 1. Here are some practice problems. As we said, a lot of 2D methods or 2D array problems are just flipping something or rotating something or just reflecting something. So it's really important to know how to manipulate 2D lists in such a way that they can't stump you no matter how they want you to rotate or reflect or deal with them. And yeah, that is it for our lesson today. So uh, are there any questions? It is 4:04. We still have we'll wait 2 minutes for any questions or even comments. You can put witty comments if you want, because
Witty comments, like, I don't know. What witty comments are there to say?
Matthew just run out of things to say. Maybe it's because you don't have any witty comments.
Wow, okay. What are you trying to say?
Well, all right. Is
Okay,
that
I'm gonna put something I don't know what that is.
what like I don't know what that is. That I cannot even start to tell you what that is.
Yeah,
'Cause
I'm not
I
sure.
have no idea what that is. Do you want to explain it, Martin? Because if it's like a funny comment, then it's fine. But if it's not a funny comment, could you explain it? Oh, it's a regex. Oh, right. See, Martin loves rejexes so much that he actually talks about rejexes in his daily life. So if you like rejexes, feel free to reach out to Martin and he'll.
have a nice conversation about
Yes,
rejects.
yes. Or image stuff too. Uh, so like today we talked about just really quickly, since I don't think there are too many questions, I'll just wrap it up in 1 minute. So what we talked about today. Oh my God, my keyboard is just dying. My keyboard just doesn't dies on me. All right, so we learned about stacks, right, and how stacks are LIFO, right? So they last in first out. We talked about queues, which are first in first out, just like a queue, like an actual queue, like a line. We have double-ended queues, which are a queue and a DQ, a queue and a stack put together. We talked about this question, the Geneva convection, and how an algorithm we would use it using a stack and a deck, right? So here's the solution again. Martin probably has a very complicated solution as well, so you can share that if you want. A dictionary is basically kind of like a map that maps one value to another one. And we have a set, which is unordered and it has unique elements, and then you remove any duplicates that exist. And then you have a 2D array, which is basically one points to different elements, and it's an array of a list of a list, which means that it's like a coordinate grid. And then you can also rotate an array by using math to find some patterns with it. And that's the end of our lesson. Uh, Thank you everyone for
Listening.
coming. Yeah, thanks everyone for listening, and we'll see you next week.